Hello everyone, my name is Lu Yixin. I am an assistant professor at Indiana University Bloomington. It's my great honor to speak at Black Hatch. This is joint work with my colleague, Professor Xiaojin Liao, and our PhD student, Haoran Lu. So today we are going to talk about the design pitfalls and security challenges in the commercial mini programs on both Android and iOS. So we are talking about a new mobile computing paradigm today. It's called app-in-app, or sometimes called the mini program paradigm. It's quickly gaining huge popularity in the past few years. In this paradigm, a mobile app called the host app, such as Snapchat, WeChat, Facebook, they support a new feature. They let other small apps run in them. So those small apps, also called mini programs or sub-apps, they run in the host app. They significantly enrich the functionality of the host app. So here is an example. This is a sub-app called Atom Tickets. It is running in the Snapchat app. So with this sub-app, the group of users in Snapchat, they can chat while purchasing movie tickets together, instead of leaving Snapchat and buy tickets individually. So with sub-apps, for example, with Amazon sub-apps, you can also place Amazon orders inside a host app. You can also use the Tesla sub-app to check a nearby charging station for your Tesla without leaving a host app. Sub-apps have been released by major app vendors and service providers such as Amazon, Tesla, Google, Starbucks, Microsoft. Such a mini program paradigm, or app-in-app paradigm, allows the host app vendor to build an ecosystem around the host app vendor, around the host app. So this paradigm has become very popular in the past few years, after first introduced by WeChat in 2017. So in this research, we studied 11 host apps that are providing the app-in-app feature. Hosting mini apps. Those host apps in total have more than 2 billion downloads. Examples of the host apps include WeChat, TikTok, Facebook. Also, we found more and more apps have started to support mini apps, such as Apple iMessage and Snapchat. So to date, there are more than 1 million sub-apps or mini apps in the wild. They are provided and released by the sub-app stores provided by the host app vendors, similar to Google Play and Apple App Store. So how do they work? How does this app-in-app paradigm work? So here we see a typical app-in-app technical architecture, which we learn through reverse engineering. So in this architecture, there is the host app, the operating system. In the host app, sub-apps run on top of the host app. The host app acts like an operating system to the sub-apps. The host app provides a sub-app runtime to run the sub-apps. The host app provides a sub-app API. So sub-app called the API to access the resources. And the host app call corresponding system API to get the resources for the sub-apps. If a sub-app API accesses sensitive resources, then the host app requires a permission check for the sub-app to call that API. So those permissions are called sub-app permissions. They are similar, or they are like those Android permissions to restrict system API. In terms of the security model in the app-in-app paradigm, first, sub-app API are restricted by sub-app permissions. Those permissions must be granted by the user to the sub-apps. So this is similar to how Android and iOS apps request permissions. Second, the sub-apps are isolated from each other by the host app. Third, the host app usually has a sub-app store that vet sub-apps They check the malicious sub-app or detect those with privacy violations. This new app-in-app paradigm introduces new security challenges. First, it is fundamentally difficult for the host app to properly manage sub-apps. In particular, the host app cannot reuse the mechanism through which the OS manages mobile apps. For example, Android uses the traditional Linux user ID to isolate mobile apps. On Android assigned a Linux UID to each app, so each app and the resources are isolated naturally by the Linux kernel. However, such a mechanism cannot be easily replicated to the host app to isolate the sub-apps. Also, the host needs to securely manage system resources delegated to the sub-apps through permission policies such as similar to the Android permission policy or iOS entitlements. However, we found that the operating system level security policies are opaque, scattered, and never organized for the host vendor to reuse. It's hard for the host app vendor to construct sound security policies that are compliant with the operating system to regulate system resources. Also, given the host limited capability and resources, it's hard for them to manage the sub-app UI model and the lifecycle, which we will detail with attacks in this talk. Another challenge is the lack of standard. We found that different host apps today have provided heterogeneous sub-app APIs and security policies, even for accessing the same kind of resources. In the absence of a standard, the sub-app API and policies can easily go wrong, unnecessarily convoluted, and which can be hard to verify and protect. So next, I will hand over the talk to Haoran, who will continue and introduce the new vulnerabilities that we found on the most popular app-in-app system in the wild.
Hi there. Yeah, thanks for the introduction. And I'm Haoran. I'm going to talk about the 4 design pitfalls we discovered during our study. So, namely, the 4 pitfalls are system resource exposure, the new overlay hazard, a sub-window deception, and the sub-app lifecycle hijacking. So first one, I'm going to talk about the system resource exposure. Ideally, in app-in-app architecture, sub-app permissions required for sub-app API are supposed to be consistent with the permissions required by the operating system when using the relevant system API as the wrap. For example, recording audios need to use the microphone, which can be accessed by the host app using the corresponding Android or iOS APIs. The host app wrap the API and provide a unified sub-app API. Since the operating system requires permission to use its audio recording APIs, the sub-app APIs should also be protected by a sub-app permission. In the example, record audio permission on Android and microphone usage entitlement on iOS are required by the operating systems. So the sub-app permission scope.record is also required by the host app. However, for the host, as a third-party app, it's very challenging to construct sound sub-app API permission policies. In our study, we found inconsistent permission requirements between sub-app API and system API, which lead to system resource exposure. An example is the unprotected WeChat sub-app API that can perform Wi-Fi scan. Wi-Fi scan can be accessed by Wi-Fi Manager API on Android and NE Hotspot Helper API on iOS. The host app, WeChat, wrap the two and provide a sub-app API, wx.getWiFi-list. Wi-Fi scan are protected through an entitlement Hotspot Helper on iOS and a dangerous level permission access fine location on Android. However, the sub-app API provided by WeChat is not protected by any sub-app permission. As a result, the sub-app API exposed the Wi-Fi scan capability to the sub-app, leaking out user location. We name such unprotected sub-app API as escaped sub-app API. Note that a high-profile host app, for example WeChat, is typically granted the location permission and many other dangerous permissions due to its rich functionalities, for example the camera and microphone. As a result, the adversary gains unauthorized access to system resources through the escape sub-app API. In addition to the example we showed here, we found many other escape sub-APIs in popular API systems, affecting diverse sensitive system resources across iOS and Android. So looking into the root cause of these escape sub-app APIs, we found two possibilities. First is the unclear operating system level security policy. And the second is the cross-platform discrepancy of permission requirement between Android and iOS. So for the first root cause, the operating system level security policies are opaque. Again, we take the Wi-Fi scan as an example. iOS protects Wi-Fi scan with an entitlement named hotspot helper. To get this entitlement, developer must file a dedicated written request justifying that the app will not have any malicious intention to get this system permission. Apple reviews the request internally and possibly assess the risk of location leakage from the app. However, the entitlement and its public information fail to show that Wi-Fi scan can cause location leakage. Such an opaque operating system level policy makes it non-trivial to construct sub-app level policies that are compliant. In addition, we found the operating system level policies are scattered and disorganized. State-of-the-art approaches leverage a program analysis-based best effort search in the Android code space to construct the Android API permission mappings. The results suffer from a surprisingly low coverage. For example, they are only able to find required dangerous permission for about half of the Android APIs. The other root cause is the cross-platform discrepancy. Since sub-app API is designed to be cross-platform, the effort to build sub-app API permission policies that are compliant with all operating systems has been complicated by the inconsistency between Android and iOS in terms of the resource protection. Consider Bluetooth scan as an example. Android API Bluetooth LE scanner and iOS API CB Central Manager provided the host app with access to the Bluetooth scan results. Host app wrap the two APIs and provide a sub-app API, ws.get Bluetooth devices. Android protects its API with dangerous level permission, access file location. In contrast, iOS does not require any permissions or entitlements on its API. In this case, what should the sub-API permission be for the host that should be required for the sub-app API? The answer is host apps usually do not require any permission on the Bluetooth sub-app API. We found that the API designer tend to leave the related sub-app API unprotected. For example, the sub-app APIs for Bluetooth scan are not protected in multiple host apps. Actually, the difference in policy level protection could result from an additional security guard put in place by the operating systems, which is unaware to the app-in-app designer. In the Bluetooth scan example, combining the signal strength and the device ID returned in the Bluetooth scan result can reveal the user's geolocation. On Android, the ID and the signal strength are returned, so the Android requires permission on the Android API. On iOS, however, one of the device ID is obfuscated, so the iOS result cannot be leveraged to reveal the user's geolocation. And so the iOS does not protect this API. In total, we tested 11 host apps, including apps like WeChat and TikTok. We found 39 escape sub-app APIs in 6 of them. These 39 escape sub-API cover 5 different system resources, including Wi-Fi, Bluetooth, microphone, camera, and iBeacon. The second weakness we found is a new overlay hazard that exists in access control management of the app-in-app system. This attack is a new type of UI redressing attack, or the clickjacking attack. Before we go into details of this attack, let's quickly go over the basic of the clickjacking on Android. On Android, the permission granting window features a protection against clickjacking attacks. That is, when the permission granting window is covered by any other windows, the user clicks will be rejected to stop any potential attacks. So the defense of this attack is that the Android will remove the overlays created by third-party apps. And Android designed a specific permission for this purpose, that is, hide non-system overlay windows. However, this permission is usually not available to host apps. The permission is designed only to be available to system apps or apps that are pre-installed by the device vendors. This leaves an opportunity for us to explore. Recall that the host apps are usually very powerful, holding a lot of permissions, and delegate them to the sub-apps through sub-app APIs. So the sub-app APIs are protected by sub-app permissions, and the sub-app permissions granting window are not protected against clickjacking attacks. So previous clickjacking attacks only target the Android's permission granting window, and in this case, we target the permission granting window of the sub-app permissions. So first, user install the malicious Android app, which can draw overlays over the host apps. And then it can launch a colluding sub-app, which does not need to be installed by the user in many host apps. The colluding sub-app will invoke the sensitive sub-app APIs, accessing the sensitive resources of the users. When the sub-app permission granting window of the host app pop up, the malicious Android app can draw an overlay and lure the user to grant the sub-app permission to the colluding sub-app. The coordination of the malicious Android app and the colluding sub-app can be through the clipboard or WebSocket and any other technologies. In total, we tested 10 host apps that are available on Android. All 10 host apps are vulnerable to our attack. Leveraging this attack, the malicious Android app can get access to the system resources like camera, microphone that are considered well protected before. The third weakness we found is the sub-window deception flaw. As a background, we first introduced the app-in-app UI model. A sub-app is displayed in a full-screen window of the host app, taking over the screen used by the host app. In the screenshot on the right, areas colored in green are controlled by the sub-app. It is possible that a malicious sub-app may fake the UI of the host app. Sensitive UI of the host app, for example, the mobile wallet UI of WeChat and Alipay, are also displayed in the area controlled by the sub-app. So, in this case, the sub-app can fake those UIs. Once explored, the sub-app can steal users' mobile wallet passwords, which can be used for making payments. We constructed a test sub-app that contains such phishing UIs and submitted it to the WeChat sub-app store and passed their vetting process. A similar UI trick can attack the web app on Chrome, or as known as the progressive web app, and the app clip on Safari. When using a web app or the progressive web app, the web app will be open in full screen without any UI of the browsers, including the address bar that can tell you the current domain you are browsing. Users can freely navigate to other web pages outside of the domain of the current web app. In this case, the browser will display a banner on the top of the screen showing the origin of the web page as a defense. In the screenshot on the right, if we do a single sign-on using Facebook in another web app, then the browser will display a banner that is showing the Facebook's URL on top of the screen. However, the web app can imitate such banner when user is not even visiting the Facebook page. In this case, the user would believe that she or he is on the Facebook website and gave out their Facebook credentials to the web app. So the problem has been acknowledged by the Chrome and Apple team. So current anti-phishing techniques that works only on app level, which focus on identify the app of the foreground window. In our attack, the foreground window is always the host app, since from the perspective of the operating system, the sub-app is running within the host app and treated as a whole by the operating system. So they will not be able to tell the difference between a sub-app and the host app. So they are not able to detect such kind of attack. The first attack we discover is the sub-app lifecycle hijacking, which is a weakness in the lifecycle management of the sub-apps. To give sub-app user a native app-like experience, the host app creates attacks for the sub-apps in the Android recent screens, in which user can quickly access apps they opened before. In the screenshot on the right is an example of the task WeChat created for their sub-app. To implement the recent screen feature, each host app needs to predefine a number of activities that will be used to accommodate the sub-app. Since the number of predefined activities is limited, the number of the sub-apps user can see in the recent screen is also limited. The limit is different for different host apps. For example, for WeChat it's 5 and for Chrome it's 8. When the limit is reached, a mandatory recycling process starts. The newly launched sub-app will replace the oldest one's task in the recent screen silently, which means the user will not know the first sub-app he or she used that is no longer exists in the recent screen. So a malicious Android app can imitate the disappeared sub-app's task by inserting a new task of its own in the recent screen, which is also known as a task hijacking attack. There are two questions to answer before we can insert the fake task. First is, what is the disappeared sub-app? The second is, when shall we insert? We found that there is a set channel that we can use to observe the sub-app launch operation in real time. So we have answers for the two questions. Each time a sub-app is launched, the host app will edit some files in the external storage that is accessible by the malicious Android apps. Usually these files are for caching purpose. We can reliably identify the sub-app being launched through those files and count the number of launched sub-apps so far to find the correct time to insert the fake task. The consequence of this attack can be various and serious, depending on the targeted sub-app. For example, if we target a health sub-app, the health information of the victim user will be leaked. And we can also get the bank credentials or travel histories of the user if we target the banking sub-app or traveling sub-app they are using. To understand the scope and magnitude of all 4 attacks we presented, we analyzed 11 most popular commercial app-in-app ecosystem on both iOS and Android, including WeChat, TikTok, Chrome, etc. All of them suffered some or all of the aforementioned attacks we mentioned. Aforementioned attacks. So to summarize, as mainstream app vendors participate in the app-in-app paradigm by releasing sub-app supports, their apps can no longer benefit from the protection offered by the modern operating systems. which have been hardened after years of open security research. In this talk, we presented the challenges in building a secure sub-ecosystem on top of the operating system, including the lack of security standard and practice in building an app-in-app ecosystem, the security gap between the underlying operating system and the limited app-level capabilities of the host app, also the lack of operating system level support. And thank you for your listening.